Yeah, welcome to Easy Mathematics and a new video. Today we discuss an interesting addition formula. We consider the function cosine x plus sine of x, and we define this function as cos of x. And what we are after is the general addition theorem for the cos function in terms of cos of the xi, and as we will see also cos of minus xi. While I do this video, I saw a video from Dr. Baker. The link is in the video description. He showed a couple of nice properties of the cos function, and he showed the addition formula cos of x plus y, and there was a nice symmetry in this, and so I decided to generalize this result. Before we start, in one of my latest videos I showed the general addition formulas for sine and for the cos function, and what I want not to do is to write the cos function as a single cosine or a single sine function, because there is this pi over 4 shift. I do not want to work with it, so we will work with cosine x plus sine of x. And the general addition theorem looks like this. We have 1 over 2 to the n, then a sum over all subsets from the set of the natural numbers from 1 to n. Then we have like alternating sign in pairs, so it starts with plus plus minus minus. You can think about the floor of cardinality of the subset over 2. Then we have a sum with n indices, j1 up to jn, and they run from 0 to 1, over a product where k runs from 1 to n, and then we have some coefficients bjk times the cos function, and then an alternating sign xk, where these coefficients bjk is 1 if jk is 0, and it's minus ex of k if jk is 1, and ex of k is defined, it's 1 if k is in the set x, and it's minus 1 if k is not in the set x. Alright, so we discussed the proof. The cos of a sum is by definition the cosine of the sum plus the sine of the sum. So in the first step we plug in the general addition theorems for the cosine function and the sine function, and you see that the products here are the same, and so we can put like terms together, and here are the even subsets, here the odd subsets, and now you can think of the signs. You will get minus 1 to the power floor of cardinality x over 2. You can think of that. It's not too hard to see. And what can we do now? In the next step we write the sine and the cosine function in terms of the cos function, and this is very easy to see that sine is cos of xk minus cos of minus xk over 2, and the cosine is cos of xk plus cos of minus xk over 2. This follows directly from the definition, and now we take care of this over 2 in both products. So k runs from 1 to n, and k is in the subset or it's not in the subset, so we have n 2's here, and we factor them out. So we have 1 over 2n and then the sum over all subsets times over this product over the difference of cos terms and the sum of cos terms. And now what I would like to do is to introduce this sine function. So if k is in x we have the minus, and if k is not in x we have this plus. So I write it as minus ex of k, where ex of k is 1 if k is in x and minus 1 if k is not in x. Alright, in the next step I want to write a symbolic sum for this difference. And we see here the alternating sign. So we have two terms, so j runs from 0 to 1, and if j is 0 we have plus xk, and if j is 1 we have minus xk, and I write symbolically bj for the coefficients 1 and minus exk, and bj is 1 if j is 0, and b1 is minus ex of k. Alright. And the last step is we use the distributive law. So we multiply out this product, and what we get is by the distributive law is n sums over j1 up to jn, and they are 0 or 1. And then we have a product k equals 1 up to n with bjk cos of minus 1 to the jk of xk, where bjk is 1 if jk is 0, and if jk is 1 we have minus ex of k. And that finishes off the proof. There are some alternative expressions, like if you want to use the expression for the cos function as a shifted sine or cosine. You can play around with that. So I hope you like this video. Have fun, enjoy, and
I welcome constructive criticism. If you have any suggestions or video requests ready, feel free to write me an email, suggestion@easymathematics.de. And if you still feel like doing math, further suggestions are now displayed. So have a great time. See you next time.